Naming aromatic compounds has some of the same rules as naming cycloalkanes, but there are a couple of twists to how we provide these names. First of all, the simplest molecule is benzene, and that has no substituents on it. And then if we have a methyl group attached to benzene, we would normally call that methylbenzene, but methylbenzene is very rarely used. Instead, this molecule is called toluene. If you have an alkyl group attached to a benzene ring, typically what we do is we either name the alkyl group by its common name or its IUPAC name. There are other groups, though, that when they're attached to a ring, basically will provide the base name for the benzene ring, and we'll see that in a few minutes. So if there's an OH attached to the ring, there's phenol. We talked about phenols in the acidity of alcohols previously. Here's a molecule that has two methyl groups attached to the benzene ring. This is actually called xylene. This could be called 1,3-dimethylbenzene, but typically it's called xylene, and this one specifically is called metaxylene. The CH3 group, this would normally be called methoxybenzene, but it has a special name and is called anisole. NH2 is attached to the ring, that's an aniline. This carbon that's attached to the benzene ring is called the benzylic carbon. That's analogous to the allylic carbon, where the carbon's attached to a double bond. So a benzylic position leads to, if there's an OH there, benzyl alcohol. If that's an acid, benzoic acid, or if there's an aldehyde, there's benzaldehyde. We also have some other benzenes that we would look at and potentially see the name for. If there's an NO2 group attached, that's called nitrobenzene. And we've already talked a little bit about if there's a sulfonic acid group attached to this, this is actually called a benzene sulfonic acid. We'll come to the specific one that we've seen before, the tosyl chloride, and I'll show you where the name comes from. So these groups then provide the base names for naming aromatic compounds. So the rules are that when we look at a benzene ring, we have to identify whether the aromatic has a parent name. So for instance, if it has an NH2, it's an aniline. If it's got a carboxylic acid, it's benzoic acid or toluene or nitrobenzene, or some the other ones that are on this slide, phenol, anisole. And so if the molecule does fall into that category, we automatically start numbering at that group on the ring. So if I'm looking at something that is a toluene, that automatically is going to be carbon number 1, and then I'm going to go and find the next substituent. So then we number either clockwise or counterclockwise to give the next substituent the lowest number. If the molecule is not a toluene, then we just go back to our rules for cycloalkanes, and we number to give the lowest sum of the substituent numbers. So if there's one of these groups on the ring, an OH, a methyl group, this anisole group, the methoxy, aniline, benzoic acid, benzaldehyde, then we automatically have to start numbering at this carbon and then go clockwise or counterclockwise until we encounter the first substituent. Of course, if there's ties, then we use alphabetization to break the tie. Now, before we do some examples, when we're naming disubstituted benzenes, we can call them 1,2, 1,3, or 1,4 disubstituted, but typically what we do is we use prefixes to short or to abbreviate for 1,2. So a 1,2 disubstituted benzene is often called ortho, a 1,3 is called meta, and a 1,4 is called para. So if I had this molecule, I would call this para-dichlorobenzene. Because the two chlorines are para to each other, they're 1,4. Suppose you could call it 1,4-dichlorobenzene, but nobody ever does that. They always call it para-dichlorobenzene. Now go back here to illustrate. Remember that when we had the this was our tosyl chloride. Well, what did the tosyl chloride stand for? Well, it turns out that this is para-toluene sulfonic acid. Only this is para-toluene. If this is an OH, then this is para-toluene sulfonic acid. If that's a chloride, then it's para-toluene sulfonyl chloride, which is where the tosyl reference comes from. So the two groups here are para, and that's just the name of this is para-toluene sulfonic acid. Okay, so you have to know the ortho, meta, and the para positions. I can guarantee you that the in-class lecture or in-class quiz over this material in the next lecture period after we've discussed it will definitely include naming the ortho, meta, and para positions. Now, if we were going to name some, let's see if I have any blank slides. If we were going to name some compounds, we might have, let's say I've got a chlorine and I've got a CH3 here. This one would be called metachlorotoluene, because this chlorine, this methyl group makes this a toluene, and it's disubstituted, and the two groups are meta to each other. You could probably call this 3-chlorotoluene, but nobody, that's sort of the really hard and fast IUPAC rule. So either 3-chlorotoluene or metachlorotoluene would be okay for this molecule. You might say, what happens if you have a molecule like this? Is this an aniline or is it a toluene? And that's actually a good question. So if you had this molecule, what would I name it? Would I name it a toluene or an aniline? In theory, you could probably think of this either way. If I made this a toluene, which I don't think it would be if it's methyl versus nitro. If it's methyl versus amine, I believe the fact that this amine group has a nitrogen in it would give it priority, at least amongst these. So in this case, I'd number here 2, 3 versus 1, 2, 3. So I believe this would go 1, 2, 3, 4, 5, and 6. This would then be called 5, no, it would be called 3-bromo, 5-methyl aniline would be its name. So if you're comparing the groups, if you're comparing two groups, you go back to your Coningold Prelog sequence rules to see if it's nitrogen versus carbon, then the nitrogen group would win, and so it would become an aniline. You'd also make the case that it would become an aniline because of alphabetization. Okay, so that's that's sort of how we name, and there's more naming rules in the textbook. Here's one that is a famous molecule. what would the name of this molecule be? And this is a toluene. So if I look at this 1, 2, 3, 4, 5, and 6, this is 2, 4, 6 trinitrotoluene, which is more commonly known as trinitrotoluene. Okay, so you have to look at the naming. You have to find one of the groups that falls into the aniline or anisole or toluene phenol categories, and then that gets automatically the number 1 position, and then you'll number clockwise and counterclockwise to give you the until you encounter the first substituent. And then if there's just, for instance, 3 methyl groups on the ring, you would want to number to give the lowest total sum of the substituent numbers if it doesn't fall into a toluene, etc. Okay. So what our next topic is to talk about the reactions of benzene rings. But before I do that, I want to talk about the groups outside of the benzene rings. I'm going to take a little diversion from that here at the moment. We know that the benzene ring is very stable. It's an aromatic ring. That means that it's very stable. Is there any way to destroy the aromaticity of this ring? And the answer is yes. It's a very old reaction called the Birch reduction reaction. If you want to basically convert the benzene ring into a non-conjugated cyclohexadiene, you need to actually add hydrogens to this ring. So we need to do reduction. And we need to do a very powerful reduction because this benzene ring is so stable. So if you think about reduction from general chemistry, my favorite is Leo the lion goes grr, which means gains electrons reduction. The oldest way to give this benzene ring an electron is to go back to our sodium metal and dissolve it in liquid ammonia. If you go all the way back to the alkyne reactions, when we did liquid ammonia reduction, sodium and liquid ammonia reduction of the alkyne, the mechanism for this was when the sodium metal dissolves in ammonia, it becomes a sodium cation and then releases a solvated electron. Well, that solvated electron is going to reduce this benzene ring and ultimately give you the non-conjugated cyclohexadiene. So this is a mechanism that I would not ask you to write, but I'll just show it to you so that you understand why we get the non-conjugated diene. So again, in the first step, sodium dissolves in liquid ammonia and it produces a solvated electron. That solvated electron, and these should all be half arrows in here. So we add the solvated electron to this carbon, and we would then actually take this electron right here, we'd break the double bond, and we would give this electron and pair it up with this one to form then a pair of electrons, which gives this C a minus charge. Then if we split this bond, one electron goes here, this double bond splits here to put one electron there, and then give this carbon one electron. So the idea here is that in the end, we've got our radical anion for this molecule, because I just gave it one electron, so it has an unpaired electron, and more importantly, it has a negative charge. Well, the reason that it adopts this para substitution is because, remember, these are big clouds of electron density. And so they want to be as far away from each other as possible. And so that's why they become para. This C minus then, in the end, if we have alcohol present, the C minus will immediately deprotonate the alcohol to put one hydrogen here. That leaves this radical, which then the radical gets another electron, another solvated electron, becomes a carbanion, and then the carbanion picks up the hydrogen from the alcohol to form the final product. So this is a 2-electron transfer to then give me a breaking up of the aromatic ring, but because of this initial radical anion structure, the two hydrogens that are added in this add para, and more importantly, the double bonds then end up unconjugated or non-conjugated. If there's an alkyl group on the ring, then this reaction will occur so that the alkyl group ends up attached to one of the double bonds. Why? That forms the more stable product, right? We want an alkyl group. We want one of those double bonds to have the maximum amount of substituents. So we can break up the benzene ring, but it really requires incredibly harsh conditions, which is a pure electron that comes about from dissolving sodium in liquid ammonia. Now, what about reactions outside of the benzene ring, particularly at this carbon right here, which we call the benzylic carbon? Well, the benzylic carbon is analogous to the carbon attached to the double bond. That would have been allylic. This is the carbon attached to the benzene ring, so it's now benzylic. If you start with a benzylic halide, it's very easy to break that carbon-halogen bond to form the carbocation, because there's a whole bunch of resonance structures you could draw for this. I could take this pair of electrons and move it here and start this process. That would put a double bond outside the ring. It would leave that carbon. It would leave this carbon with a positive charge. Wait, wrong carbon with a positive charge. It would leave the initial carbon that I wrote with the positive charge. And then I'd have my double bonds here and here. I could then take this pair of electrons, and that would give me a second additional resonance structure. Should put the plus charge there. Then I could bring this pair of electrons there and form the third resonance structure. So all these resonance structures then stabilize the benzylic carbon, the benzylic carbocation, in the same way that the allylic carbon was stabilized. If I want to do free radical halogenation, and this probably isn't going to be an X, it probably would be an R group. If we use our NBS or our Br2 and light, we're going to free radically halogenate at the benzylic position, because there are resonance structures you could draw for this benzylic radical that forms as the intermediate. So halogenating an alkyl benzene is going to put the bromine right at that benzylic position. Even if there was a tertiary carbon in the chain, it's going to brominate at the benzylic position. And of course, if we don't necessarily have an anion here, but if I wanted to do SN2 reactions, then my SN2, my nucleophile coming in and kicking off the leaving group, that's going to be enhanced because of the stability or the stabilization of this benzylic carbon by the benzene ring. So here's what I'm talking about there. In general, benzylic halides react faster than other halides. Why? Well, you've got your OH minus coming in and kicking off your iodide, and just like we did for the allylic carbons, if I drew out the transition state for this, I would have my benzene ring, my benzylic carbon with my two hydrogens here. In the transition state, the oxygen and the iodine are delta minus. That means that carbon is delta plus, and so therefore the delta plus charge is stabilized by the presence of that ring. That lowers the transition state energy and will make the SN2 reaction occur faster. Exactly same argument that we made with allylic halides and why they undergo SN2 faster. Okay, so looking at the reactions of the benzylic carbon, SN2 will be faster. You can do SN1s to form carbocations. You can also, when you brominate, you're going to brominate at that benzylic position. So the benzylic position is just analogous to the allylic position because of the stabilization of the double bond either in the transition state of the SN2 reaction or the ability to draw different resonance structures like we're doing for this carbocation. Okay. The last reaction, I believe, of alkyl benzenes or outside the ring is that if you take an alkyl benzene and you oxidize it, and these are harsh oxidizers, so these are the strong oxidizing reagents, potassium permanganate, potassium dichromate. What happens is that when you have a benzene, when you have an alkyl benzene, you basically cleave off all of the alkyl group and you convert the benzylic carbon to a benzoic acid. Doesn't matter how long this alkyl group is. It could be methyl, ethyl, propyl, could be 100 carbons long. Could be branched, could be tertiary, doesn't matter. When you take an alkyl benzene and you react it with these strong oxidizers, you convert this benzylic carbon into a benzoic acid. And so if I had a propyl group and I treated this with KMNO4, I would get benzoic acid. If I had more than one alkyl group on the benzene ring, so let's say I had orthoxylene, that's the name of this, and I treated it with KMNO4, each one of the alkyl groups, each one of the benzylic carbons would become a benzoic acid, and so I would end up with this. Okay. Now what you have to be careful of is that alkyl benzenes react with KMNO4. If I would have said, where's my empty slide? If I would have said, what's the reaction of benzene plus KMNO4, you would say no reaction. So you have to be careful that benzene doesn't get oxidized, but an alkyl benzene will. And so that's what you guys would call a trick question, but you have to keep those in the back of your mind. Benzene doesn't react, but an alkyl benzene will. Okay, so that's oxidation of the alkyl benzenes, and so there's lots of reactions that we can do with the alkyl groups that are attached to a benzene ring. Okay. Now, how would you prepare, how would you go from this propylbenzene to putting a double bond here? You might say, okay, well, how about I start by brominating this, light, room temperature. Somebody might say, but won't the bromine react with the double bonds of the benzene ring? No, right? Remember, benzene is too stable to react with bromine. So I'm going to do free radical halogenation. Where am I going to put the bromine? Right here on this benzylic carbon. So if we do free radical halogenation, I'm going to end up putting the bromine here. And then how do I get from here to there? Well, I could use either potassium tertiary or I could use NH2 minus. If you're sitting there going, well, wait, won't they give different results? No, they'll give the same result. Here's the issue. Here's the alpha carbon for this E2 elimination. Here's a beta carbon with beta hydrogens. Here's the other beta carbon. How many hydrogens are attached to that carbon? 0. There are no hydrogens there, so the only place you can form a double bond is between this alpha and the beta carbon. And that's one of the disadvantages of writing, let's say, a benzene ring with the circle in it, is that you forget that this carbon doesn't have any hydrogens in it because you forget what the circle means. So that's why I always like to write benzene with one of the two calculate structures, because then I don't forget whether there's hydrogens on that carbon or not. Now, if I added H plus and H2O, if I do hydration on this double bond, am I going to add the hydrogen, the H plus, to carbon A or B? You might say, well, you're going to get 50-50. No, I'm not. Remember, Markovnikov's rule is the overriding interpretation of Markovnikov's rule is I'm going to add the hydrogen to the carbon that gives me the most stable carbocation. So if I added the H plus to carbon A, I would get that carbocation. Okay, so that's what would happen if I added the H plus to carbon A. If I add the H plus to carbon B, what do I get? I get that benzylic carbocation. So in this case, what would happen is I would get this product almost exclusively, because the benzylic carbon is so much more stable than the secondary carbocation. So then when I added my water, remember this would happen in 2 steps, and I would get as a final product my benzylic alcohol. So that means that the benzylic carbon is special. When we start doing reactions on alkyl benzenes, we now can add, or we have to be careful that if we form a benzylic carbocation, that's going to be really stable. And if we free radically halogenate, we're going to free radically halogenate at that position because, again, the benzylic radical intermediate is going to be so stable. Okay, so you have to be careful. That benzylic position is very important and will play a role in alkyl benzene reactions. We'll do more of these in class. So those are reactions on groups outside of the benzene ring. And to be honest, there's nothing spectacular there. I mean, so the Birch reduction is new. The oxidation of the alkyl benzenes is new. But all the other reactions at the benzylic position, or that involve the benzylic position on the alkyl benzene, those are kind of review of alkene reactions. What about reacting inside the ring? Is the benzene ring so stable that it can't be reacted? No, it actually can be reacted. And the reactions that we're going to talk about for the next couple lecture periods are what are called electrophilic aromatic substitution reactions. And so the electrophilic aromatic substitution is this. Let's just say, for the sake of our argument, that I can make an electrophile that is so strong that it will actually break one of the double bonds in the benzene ring. Well, what I'm going to do is I'm going to end up substituting the electrophile for one of the hydrogens on the benzene ring. So this is called electrophilic aromatic substitution because I'm substituting the electrophile for the hydrogen. And we'll talk about this mechanism of this. And then we'll talk about different ways to form electrophiles that are absolutely strong enough to add to benzene rings. So let's say that the electrophile is strong enough to break one of the double bonds in the benzene ring. Well, what I would do is I would break this double bond and then form the carbon electrophile bond. And then, of course, this carbon would have a positive charge. There's nothing new. We've been doing that, for the better part of, months. Now, looking at this carbocation, what kind is it? Oh, it's an allylic carbocation. So there's resonance structures that I can draw for this benzene ring now that it has a carbocation in it. That's what I've done here. Looking at the green arrows, I could take this pair of electrons and move it here to form another allylic carbocation, and then move this pair of electrons here to form this third resonance structure. So this is kind of what I did. Well, it's not kind of what I did. It is what I did when I did 1, 2, and 1, 4 additions. Except in this case, you can almost think of this, if we add the electrophile here, as doing potentially 1, 2, 1, 1, 2, which would be this one, 1, 2, 1, 4, or 1, 6 addition, because I got 3 double bonds. Well, as we'll see in a minute, that's not what's going to happen. Now, these three allylic carbocations, they have this as their resonance hybrid. So what you can see, we would use our normal rules for writing the resonance hybrid. We would go through and average the bonds, and so we're going to end up with partial double bonds on 1, 2, 3, 4 of them. And then if we average charges, we end up with delta plus charges at in essence, the 2, 4, and the 6 positions. Now, at this point, you could say, well, I'm going to get 1, 2, 1, 4, and 1, 6 addition, because my nucleophile is going to come in and add to these carbocations. Well, no, they're not. Because what happens is that this ring would really like to reform a superstable benzene ring. And so what happens is that the hydrogen that's on the same carbon as the electrophile now is lost, and we regenerate that double bond to regenerate the stable aromatic benzene ring. Here's a reaction coordinate diagram that kind of shows you what would happen here. So if I add my electrophile to my double bond, adding the nucleophile would be basically 1, 2, or 1, 4, or 1, 6 addition. That isn't going to form a very stable product, because what I really would like to do is, if I lose this hydrogen, then I end up reforming the benzene ring, and that makes that final product so stable because of the aromatic ring. And by Hammond's postulate, what would happen is that activation energy would be very small to reform the benzene ring, and would be much, much larger to have a nucleophile add to any of those 3 resonance structures. So the electrophile has to be strong enough to break the benzene ring, or break one of the double bonds. And then after that happens, then we lose an H plus to give us the final product. And so that's why this is electrophilic aromatic substitution and not electrophilic aromatic addition. Okay, so we're reforming that benzene ring. So we're doing electrophilic aromatic substitution and not addition on this molecule. So what we need to do is we need to find electrophiles then that are strong enough to add the benzene rings. And so we're going to spend the next lecture period talking a little bit more about those electrophiles and how you make them. But let's just end this starting with 3 different combinations of reagents that'll form electrophiles strong enough to do electrophilic aromatic substitution. So let's say you wanted to add an NO2 group onto your benzene ring. And remember, a nitro group would have This would kind of be one of its resonance structures. So to form an NO2 plus, which would then act as an electrophile and add to the benzene ring and do substitution, the way we generate NO2 plus is to react nitric acid and sulfuric acid together. And what happens is that we end up taking the nitric acid, and again, you wouldn't have to know this, but we take our nitric acid and we end up protonating it, and then we end up losing water across this. So actually we wouldn't protonate there, we would protonate here to form that compound, and then what would happen is then we would lose water from this. We would lose water from this molecule and form NO2 plus, and then HSO4 is the counterion. So if we form an NO2 plus, that means that if I take benzene and I react it with nitric and sulfuric acids, that I would end up substituting a nitro group for one of the hydrogens on the benzene ring. We're going to start with benzene, so it doesn't matter which hydrogen I'm going to substitute the NO2 group for. That'll come a little bit later on. If there's an alkyl group or if there's a group already on the ring, then we'll have to talk about where the NO2 group goes. So this is a way to form nitrobenzene. And we'll talk about the fact that if we started with a methyl group, this is the way that people can make TNT, trinitrotoluene, if they don't blow their heads off first. And we'll talk about the reasons why that's a dangerous reaction in a couple of lecture periods. What else can I do? I can form SO3H plus and form a sulfonic acid. So what I do is I use sulfuric acid and sulfur trioxide. This is sometimes called fuming sulfuric acid, because when you take the cap off of it, there's usually a lot of smoke because the sulfur trioxide is escaping out into the atmosphere. Simple acid-base reaction. The sulfuric acid protonates the SO3 to form SO3H plus, and then we get the counterion. So this will add to a benzene ring. So if I take my benzene ring and I add fuming sulfuric acid to it, what I will end up forming is I will end up forming my sulfonic acid. Then if I replace my OH group with a Cl, then I can make a sulfonyl chloride that we used to, for instance, allow OH groups to become leaving groups. Okay, and the last one that we'll talk about for this time is halogenation. Now, benzene, taking a benzene ring and reacting it with bromine is a no reaction. Bromine itself will not add to a benzene ring. So we need to use a catalyst. And the catalyst that we use is either iron trihalide or aluminum trihalide. For instance, if this was bromine, we'd use FeBr3 or AlBr3, aluminum tribromide or iron tribromide. If we wanted to add chlorine, we would use FeCl3 or AlCl3. So these catalysts then cause the bromine to become a full-blown Br+, not some wimpy, bromine dissociates kind of to form, bromine with a little bit of a positive charge. In this case, it would completely dissociate the bromine bonds to form a Br+, and that electrophile is now strong enough to add to the benzene ring. So what you can think happening is this. You take your bromine and you react it with your FeBr3, and what happens is that the bromine takes its pair, one of the bromines takes its pair of electrons and gives it to the iron, so that we form FeBr4 minus, that anion, and then that leaves the other bromine becoming a full-blown Br+, that's now a strong enough nucleophile to add right into the benzene ring. So if you want to brominate a ring and make something like bromobenzene, you're going to use halogenation for that. Okay? So there's more combinations of reagents to form these electrophiles, and we'll be learning those along with, let's just not do reactions on benzene. Let's do some reactions on substituted benzene and what happens in those cases. And that's what we'll talk about in the next lecture period.